calculation for an ideal gas here. I'm going to do a thermal energy calculation. Suppose I have a rigid container that holds 6.0 times 10 to the 22nd molecules of an ideal gas, and it's at 0 degrees Celsius. Why? Oh, I have a rigid container that holds that much gas. Oh, yes. And I shall demonstrate that to you in just a minute. So a rigid container holds as many molecules of an ideal gas. A piston compresses the gas doing 30 joules of work. At the end of the compression, the gas temperature is increased to 10 degrees Celsius. During this process, how much heat is transferred to or from the environment? OK, here's what we're going to do. We're going to use the first law of thermodynamics. I compress the gas, and so I do 30 joules of work. And if I'm compressing it and I'm doing work, I'm putting work into the gas. So is work positive or negative? Positive, positive. So I'm going to say plus 30 joules. Oh, and the temperature increases. It goes from 0 degrees Celsius to 10 degrees Celsius. Now, for an ideal gas, thermal energy is equal to 3/2 times n times Boltzmann's constant times the temperature. So I could say the change in thermal energy is equal to 3/2 times n times Boltzmann's constant times the change in temperature. Because if you assume it's gas in a sealed container, and why not, then the number of atoms doesn't change. This is the only thing that can change. So I can work out the change in thermal energy, N times Kb times delta T. How much does the temperature change by in Celsius? 10. Except we got to convert that to Kelvin, except the difference between Celsius and Kelvin is you just add 273. So I go from 0 to 10, which means I go from 273 to 283. What's the difference in temperature? 10. It doesn't matter. If it's a difference, it can be Celsius, it can be Kelvin, all the same. And so the conversion, straightforward. And so the difference in temperature is just 10 degrees Celsius. And if I work that out, I get a difference of 12 joules. So what that tells me is the thermal energy has changed by 12 joules. I put in 30 joules of work. In order to make this equation balance, which it must, I got 30 joules there. I have 12 joules here. What has to go right here? 30 minus 12? 18. Oh, yes. So minus 18 joules. So as you do that, as you compress the gas, the temperature changes. Is heat transferred from the gas into the environment or from the environment into the gas? From the gas into the environment is the transfer that you have. Question. You come into my kitchen, and your goal is to take a cup of water and heat it up. You're going to heat up water to make yourself a cup of tea. And I say you can't use the stove. What appliance would you use? The microwave. Not so. In my kitchen, you use the blender. Oh, yes, the blender. And my blender has a 1 horsepower motor on it. As a matter of fact, if you load it, it can do 2 horsepower. It'll actually blow the circuit breaker if you load it. Oh, yes. And this is a seriously intense blender. And the reason is because you can grind up amazing things in the blender. But because of that, it's the blades are going around, and as they're doing that, they're doing work. They're like pushing on it, and there's frictional forces. And so I'm going to get a change in thermal energy, in this case not due to the addition of heat to the system, but the addition of work to the system. In my microwave, I have like a low-power microwave. It's probably about 400 watts. The blender is 700 watts. All that energy goes into thermal energy of whatever is in the blender or the microwave. 700 watts in the blender, 400 watts in the microwave, go for the blender. You can boil a cup of water in a minute in the blender. It takes longer than that in the microwave. Seriously, it's crazy. You actually have to worry. If you're like blending something, you have to kind of like worry that you don't go too fast and you can get it too toasty. This idea that you can put energy into things, or you can change the temperature of things by doing work, is something that we'll talk about. I'm going to show you a dramatic example of that. This is a fire piston. And I have it here on the front. And the picture looks like this. And I'm going to change the thermal energy of the gas in the piston by doing work on it, just as we talked about. I said you have a gas in a rigid cylinder, and I have a piston, and I do work by pushing the piston and compressing the gas. Oh, yes. This is exactly what's going to happen. Piston goes right in the top here, and it's a really, really tight-fitting piston. There's a piece of cotton inside the cylinder, okay? Piece of cotton. And it turns out cotton will spontaneously ignite if the air temperature is high enough. And if I very, very quickly compress the cylinder, and when I compress it really quick, compress the air in the cylinder really quickly by pushing down the piston, if I do it fast enough, there's not time for heat to go from the air into the cylinder. And so as a consequence, the thermal energy of the gas inside the cylinder increases dramatically. What happens to the temperature? Temperature increases. It increases enough to actually set the cotton on fire. Oh, yes. And so I'm going to do this, and I'm going to dim the lights. I'm going to turn them all the way off. Turn them all the way off. I got my cylinder right here. And I'm going to push down on it, a count of 3, and I want you to watch for the flash, and the flash is the ignition of the cotton ball. 1, 2, 3. And that was igniting cotton because the air temperature was high enough, and the air temperature was high enough because I did that. I put work into the system, increased the thermal energy of the gas, and the cotton caught fire. And as a matter of fact, if you want to come look at this later, you'll say, where's the cotton? It's gone. It's all consumed in the flames here. There's just smoke that remains. It was completely consumed. You can buy these.